Okay, for the second part, let's continue with PDEs, with our partial differential equations. We are going to continue with the same parabolic equation we were looking, but now we are going to change the medium we were studying. So if you remember, we had this bar from, say, 0 to a, and we had some partial differential equation on that. The equation was the second derivative of a function u with respect to x is equal to a constant, we're showing that with 1 over k, times derivative of that function with respect to t. So we were showing x with this direction, in this x direction, and this was a bar. So this is the first example, was the case where this bar is finite, right? That's what we studied, and you studied that pretty well for your exam. Now there are two other more cases. So it's either finite, which we already seen that, or it's semi-infinite, which the bar looks like this. It's bounded from left, but at the right, from right, it goes to infinity. There is no bound on the right-hand side. It continues to infinity. And the other one is infinite from both directions. So the bar looks like this. So it goes from left goes to minus infinity, on the right goes to plus infinity, right? So in the first case, we have two boundaries, right? We have two boundary points. One is when x is equal to 0. One is when x is equal to 1. In the second case, we have one boundary point, and the other is kind of, we call it usually the asymptotic condition. It goes to infinity. There's no boundary anymore. It's kind of, in the sense, it goes to infinity. Sometimes it's called the asymptotic condition. In the last case, there is no boundary. There are just the asymptotic conditions. There is no boundary points, right? Equations are the same. The domain of this function u is changing, and of course the boundary conditions, right? So let's kind of consider both of these things. So the finite case, we've already solved that. So let's go on to study the semi-infinite case, where we have a bar like this, goes from 0 to infinity. So we have this function u, its second derivative of u with respect to x was equal to 1 over k derivative of u with respect to t. So x is greater or equal than 0, it's less than infinity, and t was positive. We had a boundary condition at 0, so we know, let's say the boundary condition is this. U at 0 at the time t is equal to 0. So we have the boundary condition here. U of x and t, this is kind of the asymptotic condition, is bounded as x goes to infinity. So there is no boundary condition here in that sense. The asymptotic condition, it says this u, which you can think about it as temperature, doesn't go to infinity. Or it's not unbounded, it's bounded. And then we had the initial condition, u of x, for any point x at the time 0 is given. F of x, where f of x is a given function. And we wanted to solve that. So the first steps of the solution are completely similar to the things we've seen before. We would use the product method to assume that we can write down u of x and t as a function of x times a function of t. The first few steps don't change. There is no difference in the first few steps. So just like before, we get to this step that we understand the second derivative of f over f is equal to derivative of t. Note that the left-hand side derivative of f, of course, is with respect to x, and on the right-hand side derivative of t is with respect to time t. This is equal to constant. Just like before, we would learn this constant is negative. These things are just like the case we have seen before. There is no difference yet. So this constant is negative, so we show it with negative lambda squared. And just like before, we would get two equations. The second derivative of f plus lambda squared times f equals 0 for some lambda. And then derivative of t with respect to time plus lambda squared kt is also equal to 0. Okay, great. So let's look at the first equation again, like what we had before. We have a sort of general solution for these equations. This is a homogeneous ODE, second order ODE. So in general, solution was something of the form C1 cosine of lambda x plus C2 sine of lambda x. Now we have one boundary value condition. So remember that we knew u of 0 and t is equal to 0 because u is equal to the product of f and t. It tells us f of 0 is equal to 0, but the thing we have above tells us f of 0 is equal to c1. Therefore, c1 is equal to 0, and therefore this term does not appear in the solution. So up to this point, everything is like the finite case. The difference now is that there is nothing left. So usually the other boundary condition used to tell us, it was giving us more information, especially about lambda. There is no more information anymore. There is no other boundary condition. So that's what we have now. So the result is f of x. Well, up to the constant C2 doesn't matter. So up to constant, it's equal to sine of lambda x. The other asymptotic condition, if we just go one page back, was telling us u is bounded. This tells us f times t is bounded. Therefore, well, let's assume it tells us that f is bounded. But you can see here that this function is always bounded. It's independent of lambda. It's always between +1 and -1. So this is bounded. So this being bounded doesn't give us any new restriction. This is bounded for any lambda. So any lambda is potentially a good lambda, which we can choose here. In the finite case, if I go back, in the case where we had a finite bar, it wasn't going to infinity, there was some strict condition on lambda. So we could have lambda 1, lambda 2, up to lambda n, and after that, there were infinitely many different values of lambda, which could appear in this equation, and we would have solution corresponding to them, f1, f2, etc. But those lambdas, they were very explicit one. For example, in this case, in the simplest case, which the boundary condition was 0 at both ends, lambda n was equal to n pi over a, very explicit. So we had a discrete set of solutions. So in another sense, there are infinitely many lambdas, but they are countable. Here, in the case where this goes to infinity, any lambda is acceptable. There is no condition anymore. So every real number lambda is acceptable for us. So any real number lambda in R is acceptable, and we would have a corresponding function f lambda, which is sine of lambda x. So any lambda is acceptable. So we have now uncountably many possible values for lambda. Okay, that's the real difference. So here we would have countably many eigenvalues. Here we have uncountably many eigenvalues. Okay, because the other boundary condition used to give us a condition on lambda, and that condition gives us some specific values for lambda. There can be infinitely many, but they're always countable. In this case, being bounded doesn't imply any new condition on lambda. Any lambda is acceptable in R. R is uncountable. We end up with uncountably many values for this lambda. Okay, great. So that's the case now. Any lambda would work. Just one thing: if lambda is negative, for example, let's show lambda 1, or maybe let's say lambda is -1, for example. Then the corresponding function would be sine of lambda x, which is -x, which is equal to minus sine of x. So this is not linearly independent. This is not linearly independent from sine of x, right? So we already, if f of 1 is equal to sine of x. So considering negative numbers for lambda doesn't give us any new solution if we are only interested in linearly independent solutions. So we can just consider the non-negative ones, right? Because if it's negative, the negative sign just comes out of sine. Just you can absorb it into the constant behind it, right? So I would assume only that lambda is non-negative. Still, they are uncountable as we know that now. Great. So on this bar, which it goes from 0 to infinity, for any lambda non-negative, well, positive, because if lambda is 0, sine of lambda x is also 0. We have a function f of lambda of x, which is sine of lambda x. This function satisfies the equation we had for f. Let's go back. This was the equation for f. And we had two boundary conditions. One was telling us f of 0 is equal to 0. The other one was telling us that f is bounded. Sine of lambda x satisfies both of them for any lambda. Here we are assuming lambda is positive. So we have infinitely many solutions to that equation. Not 1, 2, or we have infinite. For each lambda, we have one of them, right? But because we can change also lambda, we would get infinitely many. And that infinitely many is uncountable because lambda can be any positive real number. Okay, have that. Now going back to t, the equation for t was t prime of t plus k lambda t of t is equal to 0. This one is pretty simple to solve. This is just by separation of variables. We have done this before. The solution is of the sort e, this is lambda squared. I guess minus k lambda squared t, yeah. Okay, so for any lambda, we get another solution of t. So I would just write lambda here. Any lambda gives us one t lambda. So there are uncountably many of these functions t lambda 2. If we multiply them, f lambda of x times t lambda of t, we would get sine of lambda x e minus k lambda squared t. We would get one solution for u. Remember, we were assuming we can write that u like this. This thing satisfies the equation we had for u. The equation we had for u was the second derivative of u with respect to x is equal to 1 over k derivative of u with respect to t. Each of these things satisfy that. But for each lambda, we get one solution for this equation. In order to show they are distinct, to differentiate them, I add this index lambda. So for each lambda, say for each positive lambda, we have one of these solutions. Okay, so there are infinitely many solutions to this equation. And not only there are infinitely many solutions, again, there are uncountable of these solutions. Okay, now we can see the real difference here. In the case where we had finite bar, we were ending up with lambda 1, lambda 2, lambda 3, etc. We have countably many eigenvalues, and we had f lambda 1, which I would just show it with f1, f2, f3, and t1, t2, t3. And so in general, fn, tn, corresponding to lambda n, we were multiplying them. We're getting a solution, and we wanted to consider the kind of the total solution, the general solution. We are considering their linear combination, and we were saying all this. We can write in some sense every solution as their linear combination. Now, in this case, which this bar is infinite, for any positive lambda real number, we have one f lambda and t lambda, and their product is a solution. But they are not countable anymore, and the sum of uncountably many things doesn't make sense, at least in the usual way. So when we are talking about sum in this course, we are always assuming they are numbered, f1, f2, f3, etc. Then we add them. If you have uncountably many things, their sum doesn't make sense. Their linear combination with the sum doesn't make sense in the usual way we know, as we know. So rather than fn, we have f lambda for any positive lambda. Rather than tn, we have t lambda for any positive t. They have some coefficient. We show that coefficient with b lambda. Rather than adding them, looking at the sum, when continuous thing, the infinite but countable becomes uncountable, you usually replace sigma with integral. So rather than the sum of Cn, Fn, Tn, we should look at the integral of b lambda, f lambda, t lambda, d lambda. And lambda can be any positive number, so it goes from 0 to infinite. So that would be the general form of the solution. So u of x and t would be the integral from 0 to infinity, b lambda, the coefficient. This plays the role of Cn in the linear combination in the previous case. Sine of lambda x, e to the minus k lambda squared t, d lambda. So this is the form, the general form of the solution we can find here. The only unknown is this thing. How can we find this one? We can find this one using the initial condition. Okay, so remember the initial condition was telling us u of x and 0 is equal to f of x for some given known function x. What is u of x and 0? Sorry, yeah, what is u of x and 0? So it means we should let t to be 0. We have t here. We should take the variable t to be 0. So with the integral from 0 to infinity, b lambda sine of lambda x. E to the 0, that would be equal to 1, d lambda. On the other hand, it's supposed to be equal to f of x. For any positive x, we should have this. We want to have this equality for any positive x. We want to have this equality. Okay. Great. So I want to use this thing to find b lambda. What is b lambda? How can I use this thing to compute b lambda? Does anyone remember? We have seen something very similar to this thing before. Does anyone remember where we saw something like that? some equation like this. We have seen something very similar and we solved it. It wasn't Fourier series. You are very close, but it wasn't. You're both right. Very related to Fourier series, but it wasn't Fourier. In Fourier series, we had this thing, but we had sigma here rather than integral. Fourier integral, yes, exactly. We saw exactly same thing when we were computing Fourier integral. If you remember, we multiplied both sides by sine of lambda x. We took integral again. We interchanged the integrals and things like that. I wouldn't repeat that again. I would just write down that. So similar to what we did in computation of Fourier integral, we can do that here, and we would see b lambda is equal to the integral. We have a constant here, 2 over pi, integral from 0 to infinity, fx sine of lambda x dx. This integral is with respect to x. So assuming we can compute these integrals, we can compute this number b lambda, we can compute them. We can write them down here, and we would get the other integral. And assuming we can compute that integral, that would be the solution, the general form of solution we would get for that equation. Okay. Is there any question here? Okay, we have a very similar problem in the homework, similar to this one. We have an infinite rod, semi-infinite rod. This f of x is given. I think maybe in our example, it's something like sine of x. I don't have that in mind. And I asked you to solve this thing. So you should go all of these steps, and here you should, so I think, for example, f is maybe sine of x. You should compute this thing for that specific f I've given in the homework. And then you should bring it here and write it here and see what you would get. The other case we like to study, we still have a little time. Let's try to study the last case too, is the case where we have an infinite bar in both directions. So this time, this bar goes to plus infinity on one side and minus infinity to the other side. There is no boundary conditions anymore. So we have the same equation. There is no boundary value condition anymore. So the only thing we would say is that u of x and t, if x goes to plus infinity or if it goes to minus infinity, in both cases it is bounded. There is no 0 or a anymore. And then we have the initial condition, u of x at the time 0 is given, f of x. Again, this f of x is a known function, it's given. Sine of x, some trigonometric function or something else. Usually in many examples, it's a trigonometric function. So we do everything again similar. We would write down u as product of two functions, just like we did before. We would see that if we do that, the second derivative of f, which is over f, would be equal to t prime over t kt, should be constant. Again, we see this constant here. It should be constant. This constant should be negative. Again, we can show that. So these things don't change, right? And we get the same equation. Now, we solve this equation just like we did before. We get c1 cosine lambda x plus c2 sine lambda x. So if you remember, when the bar was finite, for example, if we had, let's say, u at this point is 0, it was making one of these things 0 or one of these things, we understand what is the value of C1. The boundary condition, the other one, at least in the examples we saw, was giving us, for example, the other, let's say C2, the value of C2 or something about, something about lambda. But now, when we moved to the case where in one side it's infinite, we didn't get anything about lambda anymore. Now, in this case that there is no boundary condition, we wouldn't get anything about C1 either. There is no condition, right? So in the previous example, if we go back here for a second, we learned C1 is 0 because C1 happened to be equal to f of 0, and the boundary condition told us f of 0 is 0. So we understood C1 cosine does not appear. Here we don't have that anymore. There is no 0 anymore. We only know the function f is bounded. Let's say u being bounded, let's say it implies f being bounded. Well, it does, because we know what is the other function t. So it does, and these functions are bounded. So we don't get anything new here. We should keep both of these functions, sine or cosine. So the general form would be something times cosine plus something times sine. So the general form of function f of x would be, I would show that with some coefficient times cosine of lambda x. Let's show that with a of lambda, and something times sine of lambda x, show that with sine of lambda x. Again, here, any lambda is acceptable to us, any lambda in R. Negative ones don't give us anything new, because you can minus sign, either cosine, kind of get rid of the minus sign, or minus sign comes out of sine. You can absorb them into a and b. So we can assume lambda is, say, positive or greater or equal than 0 to get that a lambda a naught 2. Okay, so anything is acceptable. We have infinitely many of these things, and they're again uncountable, and we would have a lot of these things. And then we would solve t just like before. I would show this with f lambda and t lambda, and we had e to the minus k lambda squared t. Infinitely many of these solutions, we multiply them. So we multiply f lambda x, t lambda t, we would get this thing, a lambda cosine lambda x, plus the other term, b lambda sine lambda x times e to the minus k lambda squared t. Each of these things, for each lambda, is a solution to the equation. For the original equation we had for u, for suitable choices of a and b. So each of these things potentially can be a solution, actually. I show that with u lambda. So again, rather than having a linear combination of these things and having a sum, if there were finitely many or there were countably many of these lambdas, we would define u of x and t to be linear combination of these things, right? But not that they're not countably many, they're uncountable. We can take their integral, actually. So here x actually can be anything from minus infinity to plus infinity here, and lambda is any positive or, say, non-negative number. So lambda can be anything from 0 to infinity. Great. If we have an extra condition, we can apply that. So we have extra conditions. So you are the condition you are saying you have x and 0. That's the initial condition. We will use that. We will use that, and we will see that initial condition would tell us something about A and B here. That is correct. That's correct. Yeah. We will get there. You are completely right. So in general, the form of the solution should be something like this for suitable choices of A and B. So what are A and B? That's exactly where the initial condition comes. So if t is equal to 0, if you let t to be 0, you would get u of x and 0. But the initial condition told us that's equal to f of x. On the other hand, if in this description of u, we let t to be 0, we have some t here. If we let t to be 0, e to the 0 becomes 1, we would get the rest. It would be integral from 0 to infinity, a lambda cosine lambda x plus b lambda sine lambda x, d lambda. Now we want to compute A and B. This is exactly what we did again in order to find the Fourier series of a function f. You can write down the Fourier series of f to see what are A and B. I would remind you what are the things we would get here. So A lambda and B lambda, they can be written from the Fourier series of f. A lambda would be so there's a small difference with the previous case. In the previous case, x was between 0 and plus infinity. In this case, it's between minus infinity and plus infinity. So the integral would be from minus infinity to plus infinity, f of x cosine lambda x dx, 1 over pi. Okay. In the previous case, it was 2 over pi because integral was from 0 to infinity. If you go back to Fourier series, you would see why these two cases are different. What's the source of difference? Great. So we have these descriptions for A and B. So we have another similar example in the homework. Again, f is given. Any lambda is acceptable. You can just write these things down. You can compute these integrals, and then you can plug them back into the solution. Plug them back into this equation, right? This is the final answer. You can just compute A lambda and B lambda and write them here to see what we would get. And you can potentially take integral with respect to lambda. If it was hard, if you couldn't get that, it's fine. I don't remember now if it's really in our homework, if that's doable or not. You can try to see if you can do that. So that's the case. So we kind of considered all three. Yeah, the integrals do go to infinity because for x, x goes from minus infinity to plus infinity. And the way we thought about lambda, it goes from 0 to plus infinity. So we studied this equation on the finite bar, semi-infinite bar, and completely infinite bar from both sides. And they have different forms. Great. You have some homework about that. I hope it'll help you to understand this better on Wednesday. So we wrap it up for your homework. Now you know everything you need to know for your homework. On Wednesday, we would start with the wave equation. Is there any question? Okay, great. So it's a good place to stop the class.